Welcome to lecture number 17, which is the concluding lesson on process control of this course on industrial automation. So, in this concluding lesson, we shall look at two things. We have seen the PID algorithm, we have seen several control structures. Today, we are going to talk about the implementation issue. If you really want to make a control loop work for a process, there are several things that you have to do. If you go to buy a PID controller in the market, you find controllers with several features and you briefly need to understand them. And secondly, because since we are closing our important module on process control, so we will take a bird's eye view of control again and mention certain facts which we have to remember, because while we study control in engineering, typically electrical engineering, we often focus on we often focus very intently on one part of the control problem and tend to neglect the others, but they are very, very important parts of control and I would like to draw your attention to them. So, that is the purpose of this lecture. Instructional objectives are firstly, describe typical features of an industrial controller, what you might expect in a typical controller. There are lots of variations, but we will only have the opportunity to look at a particular case. There are various variants of the PID equation. If you read the PID equation, sometimes you feel that is the only variant and you might implicitly assume the same variant to be existing in your controller. That is not the case. The several manufacturers implement PID controllers in various ways and you need to understand that before setting gains. Describe major practical features of PID controller implementation. If you want to build a PID controller, then there are certain facts that you need to pay attention to. So, those things, and understand the factors that limit control performance in the feedback loop. So, one needs to understand what is possible, what is not possible, what causes problems before being able to make control work for a particular process. So, let us begin with the implementation issues. So, let us first look at an industrial PID controller specification. This is a very typical specification. This one is adapted from a Honeywell PID controller, which is very Honeywell is a very standard company, very well known company in the field of process control. So, we have several features. First, with that you have, it says that you have PID with alarm and relay outputs. So, you could depending on process conditions, you could set certain alarm outputs. Maybe it will lighten up some annunciation, or it will ring a buzzer, and it also provides some relay outputs, so that if you need, you can switch off things or transfer it from automatic to manual. You can do various things. Configuration in engineering units is very important, because generally the process control engineers, they are not electronics people, neither are they always experienced control engineers. They are generally plant engineers. So, they understand things in the domain of the process. So, it is important to be able to understand gains, times, outputs and inputs in terms of the engineering units of the process. So, if you are taking a flow feedback, then somebody might be interested in knowing that what's the flow in, let us say, meter cube per minute, rather than actually the feedback is coming as possibly as a voltage or a current 0 to 5 volts or 4 to 20 milliamperes. But learning it will be a lot easier for the process engineer if everything is expressed in terms of engineering units. This may seem trivial when you are studying an engineering course, but they are very important in the field. there is most PID controllers will support communication, standard communication using standard communication protocols like RS-232 and RS-485. So, these are used for a variety of purposes. For example, provision for SCADA interface. SCADA stands for this one, which is a white pen, supervisory control and data acquisition It means that the controller can be in the field close to a machine or in a separate place, while the controller can be monitored from a different place, maybe a central control room. So, if you want to do that, then you need to have a supervisory control and data acquisition interface, by which sitting in the control room you can monitor the controller and see the performance of the control loop. So, this is usually provided. This can be done using these communication standards and interfacing it with a PC, and then using a visualization standard, visualization software. There are very good visualization softwares available on the PCs, so you could use them. Then there are facilities for temperature time. This particular controller was mainly built for a temperature control application. You will very many times you will find that controllers are marked as temperature controllers, flow controllers, pressure controllers. So, they may be all PID controllers, but they are marked as such because of certain reasons. For example, first of all, you will find that they will be able to take inputs of that particular kind, right. So, for a temperature controller, probably there will be a direct facility to interface thermocouples or RTDs. Similarly, for a flow controller, there will be a direct interface to a flow sensor. That is possible. Second thing is that realize that temperature, flow, pressure, these control applications typically work at different bandwidths. So, while a temperature controller may be adequate to have a temperature controller which is within say 10 hertz. For flow control, you may require a bandwidth of something like 100 hertz, and for pressure control you may require even higher bandwidth, something like maybe 500 hertz. So, the devices themselves, that is the electronics inside, everything is to be made according to that. So, you might have you might have an anti-aliasing filter in the controller, and the anti-aliasing filter bandwidth will have to be decided by the sampling time, as we all know, and this may be decided based on what kind of control it is. So, the anti-aliasing filter for a temperature controller is likely to be quite different from that used for a pressure controller, right. So, this is a temperature controller that we are seeing here. So, there is a facility to provide a temperature time profile set point ramp. There could be certain processes where you don't need to keep the temperature constant. On the other hand, you need to maybe keep it constant at T1 for some time, maybe 10 minutes, and then ramp it up to T2 within 2 minutes, and then keep it at T2 for 20 minutes, and then ramp it down to 0. So, such temperature profiles need to be set up for various chemical processes, because they are often very temperature sensitive. So, here they have provided a facility by which you can actually set up this set point ramps and their temperature time profiles. That would be very useful in this case. Similarly, processes keep changing because of their characteristics. Furnaces, fire lining of bricks degenerate, heat transfer coefficients change, depositions. Typically in heat exchangers, heat transfer coefficients tend to change because of depositions. For example, in let us say there is a plant where you say in the Middle East, people make drinking water by using seawater. So, that is called a desalination process, and it turns out that there is huge amount of, it is a very energy intensive process, and the heat transfer coefficient is very important. So, that incidentally the heat transfer coefficient tends to change because there are in the pipes you get depositions from seawater. So, in such cases you, for efficient response as well as for things like energy efficiency, you need to tune PID controllers from time to time, and that is, so they have provided algorithms for doing that using, this fuzzy means there is a special technique called fuzzy set theory, which is used to design controllers. So, you can have fuzzy and adaptive tuning. Adaptive tuning means that the controller continuously keeps adapting as the plant changes. So, you could choose one of these to get the PID settings. You could use some special purpose alternative control algorithms which the manufacturers are providing in a bundled fashion. So, they are actually, they have some experience, they have designed some algorithms which work well in certain applications. So, they are providing you some alternate control algorithms, maybe some variants of PID. So, you are free to use them if you want. Then sometimes you may require two different sets of PID parameters, and you need to have, so you need to give dual set points. So, on the same process you could use two different PID parameters, maybe depending on two different modes. For example, there could be, for example, suppose there are heat cool PID controllers. Okay. So, sometimes the same device has to heat, let us say building, let us take a heating, ventilation, air conditioning, HVAC application. So, down in the basement you have the heater which will probably operate basically control a steam boiler, or you could have a chiller which will operate the centralized air conditioning using cold water. So, you could use, so both of these may be controlled from the same controller box, but since these are controlling two different equipment, so it is obvious that two different sets of PID controllers will be required, and for them you might need two different set points. So, such facilities have been provided here. And finally, you could have remote set point operation, where basically this remote set point is actually a subset of SCADA. So, if you have supervisory control from a remote place, then you could give set points, maybe the operator sitting in the control room can give set points. Okay. So, this is what a typical PID controller looks like, and if you look at its input outputs, for all controllers input outputs are very important. So, it provides 0 to 5 volt DC or 1 to 5 volt DC. 1 to 5 volt DC sometimes provided to detect wire breaks or shorts to ground, or you could have 4 to 20 milliamperes, or so you have two inputs. On one of them it can take 0 to 5 volt or 1 to 5 volt DC and 4 to 20 milliamperes, and in the other input it can take 1 to 5 volt DC and 4 to 20 milliamperes, and as output it can provide 0 to 5 volt DC and 4 to 20 milliamperes. And similarly, it can directly take type K thermocouple or PT100 RTDs. It can give digital alarm outputs, or it can also give relay outputs in the form of NO and NC contacts. And all these that you have are actually configurable. You can actually view the configuration, you can change the configuration and set the controller. So, this is a typical industrial PID controller. Having seen that, let us remember, let us come to this point, that what is the PID controller and what are the interpretation of its gains. It turns out that there are several PID controllers which are several forms of the PID equation which are in use in the industry today. So, for example, you have this form which I call form 1. You have the other form which is form 2, which is probably the most popular in textbooks, and form 3 which is a rather which is an abstract control systems kind of form, typically if you ask an electrical engineer, he would like to see it in this form. Okay. So, while chemical process engineers will probably use this form and these two forms. So, as we know that in this Kc, Kc dash, Kc double dash all stands for controller gain, Ti is integral or reset time or 1 by reset rate, and Td is derivative time, and Kd is derivative gain, right. So, sometimes here we have a Kd. So, this Kd is used for a certain purpose. We will discuss it right now. So, you see that we have 3 different forms. Why is it? So let us look at the first form in slightly more detail. You need to understand and you need to find out which of these forms your PID controller is using, because if you mentally assume that it is using one of the forms with which perhaps you are familiar, and if the controller is actually using another form, then the gain settings that you are going to compute are not going to be right for that form. Okay. So, let us look at form 1. Actually, it turns out that form 1 is sometimes called the series or interacting or classical form. The reasons for these names is that firstly series, that you can understand that this is in series. So, this is one term and this is the other term, okay, and this is the other term. So, there are 3 terms which are getting multiplied. So, therefore, they are in series. Why is it interacting? It is interacting because, for example, if you change with respect to the second form, which is probably the most popular, if you change any one of the, let us say if you change Kc, then integral time and basically the integral and the derivative gains will change. If you change Ti also they will change, if you change Td also they will change, and then all of them will change. So, you see that they interact, that is you cannot independently, unless you do it very carefully by actually solving equations. If you just change Ti, then it is not just that the integral time is going to change, the derivative time will also change and the proportional gain will also change. So, therefore, the changes are interacting with one another, and that is why it is called an interacting controller. This is called analog because this controller has its origin in the old days pneumatic controls. Actually, it turns out that it was easier to generate the PID equation in this form using pneumatic elements, things like orifices and then bellows, flapper nozzles. So with such things it is easy to build it in this form and not in the parallel form, right. So therefore, it is called analog and classical. So similarly, so basically this form came or originated from the pneumatic controllers and still persists. Most major vendors of digital controllers provide this form of the algorithm because again legacy is going on. Okay. So, if you look at the second form, this is the most common. It's called non-interacting, although it is actually partially non-interacting in the sense that if you can change Ti without affecting Td and you can change Td without affecting Ti. However, if you change Kc, both Ti and Td are changed. So, to that extent it is partially non-interacting. It is called parallel because rather than having multiplication of 3 terms, here you have sum of 3 terms. So, you have sum of 3 terms. So, that is why it is called parallel, although there is a multiplication. So, it is again partially parallel. Sometimes IDEAL or ISA means Instrument Society of America. I do not know whether how far these IDEAL or ISA are so valid. It is used in most of the textbooks, and if you now you could try to convert, right. So, what is the relationship between form 1 and form 2, for example? So, it turns out if you solve by equating coefficients of s in the numerator and in the denominator, then you would find very easily that Kc dashed, if you there is a catch. That catch is that if Kd is high, that is that 1 plus that is this factor. Let me just go back. That is this factor, this particular factor if you ignore, then it turns out that you can match the gains, right. And how do you match the gains? So, you match the gains second form. So, if you so it turns out that you get such formulae that Kc dash turns out to be equal to this, Ti dash turns out to be equal to this, and Td dash turns out to be equal to this. So, you see that if you set gains Ti and Td in the first form, you are actually setting, if you set Ti, Td and Kc in the first form, then the actual gain, which sometimes is called the effective gain and the effective integral time, will be actually obtained according to your understanding. Suppose you have read this equation and you are going to a controller which implements in the first form, and if you set some values, then the actual values which will be realized will not be equal. So, that needs to be remembered, all right. So, in fact, interestingly, it turns out that sometimes you get absurd readings. For example, if you set some value in the second form where Ti dashed is less than equal to 4 Td dashed, if you want to set, you actually cannot set it in the first form, because it turns out that if Ti dash is less than 4 Td dash, then Ti Td values are complex. They are not you won't get real numbers Ti and Td which will be able to realize this. So, you see the first form is somewhat constrained. On the other hand, the second form, in the second form there is no, the second form does not have that 1 plus that denominator with the derivative term. So, there is that denominator is actually used for limiting the derivative gains, as we have pointed out earlier, that the derivative gain needs to be checked because of the fact that the sensor signal may contain noise, and then the derivative will give you very noisy signals. If you try to differentiate noisy signals, we get very noisy signals. So, there is a need to restrict the high frequency gain of the derivative, so that noise is not amplified while the process signal gets differentiated. So, that is possible in the first form, while in the second form it is as such not possible, but you could add such factors. For example, you could add that factor by adding such a term. So, by adding such a term with the overall equation, or by adding that term only with the derivative part, one of these two things you can do. So, if you look at the third form, that's the most quote unquote theoretical form. It's close to the second, but it's completely parallel in the sense that the three coefficient Kc, Ti and Td are totally decoupled. You can change any one of them without changing the other. So, in that sense it is completely parallel and completely interacting, and to stress the fact that even even Kc is not interacting, it is sometimes called gain independent, and these are the standard equations which you get so this is the relationship between the third form and the second form. You already have a relationship between the second and the first, so you can substitute and get the other one, and you can similarly do a derivative limiting by having another lag term with the derivative term. So, this needs to be understood that PID equations come in different formats. So, now let us quickly run through some of the just putting the PID equation isn't going to be enough. Okay. So, we first looked at the hardware of the PID controller, we have looked at the PID equation, and now we are going to look at some of the software features of the PID controller, so that we have some idea about the whole PID controller implementation. So, you have I will just list them. They are in no particular order, and some of them you have already seen. So, this you have already seen that the option to have the derivative function act only on the process variable and not on set point changes, because set point changes can be step like. So, that would give suddenly induce a very high input to the plant. So, the input will rise like almost like an impulse and will come down if you make a step change because of the derivative term. So, you never apply the such set point changes on the derivative term, but you take the derivative term through the only from the process variable. So, you need to provide provision for reset wind-up protection, this we have discussed in detail. You need to provide bumpless auto manual transfer, this also we have discussed. Sometimes apart from there are in a controller there are different kinds of filters which are used. So, one filter is to limit derivatives. You could use special purpose filters not to excite certain modes of a process which are very oscillatory. For example, if you are imagine that if you are if you are having a container which contains molten steel, liquid steel, and if you try to move that container, then what will happen is that the steel surface will try to move and it might spill over molten steel. So, you need to construct, so for such operations which are typically used in steel melting what is called basic oxygen furnaces, which have to be tilted where the molten steel has to be slowly moved. So, for such controllers standard PID control is alright, but apart from that just before the actuator you put certain filters such that those oscillatory modes, this liquid surface spilling can be linked to a resonant behavior, very highly undamped very lowly damped oscillatory behavior at a certain frequency. So, you do not want to excite that. So, you do not want to give input at that frequency. So, for such purposes you sometimes use notch filters which will pass all signals, but only in a very so they have they have gain characteristics over frequency, I am sorry, somewhat like this So, in this range they will pass control signals, in this range also they will pass control signals, but in this narrow range they will stop the signal. So, if you have your resonant frequency in this range, this is omega, this is say u omega, j omega. So, in this range this notch filter, rather this is actually gain of the notch filter. So, it is g j omega. So, in this range the notch filter will not allow any inputs to come. So, such things need to be done. You need filter for anti-aliasing. You are probably aware of this, that after all these PID controllers are actually digital devices now today. They all contain microprocessors and they will do all kinds of computation using digital signal processing methods. So, it is well known that if a signal is sampled, then its analog spectrum gets repeated. So, you can these are very standard signal processing phenomenon. So, if you take a signal which is low pass, so its spectrum, this is omega minus omega, complex spectrum we are talking about. So, if a spectrum is like this, then and if you are sampling it at this rate, then it gets repeated. Actually, the spectrum of the sampled signal is going to be repeated. So, it will be repeated indefinitely. Okay. So, now imagine that if you make the sampling frequency low, then it turns out that suppose now I am just exaggerating the other way. Suppose the signal has this bandwidth and you are filtering it at this frequency. Then these lobes will now come and start overlapping. So, this will be one of the lobes and probably this will be the other lobe. So, what will happen is that effectively once these two lobes, if you take summation, then you are going to get a frequency spectrum of the digital signal will look something like this. So, you see that, but this is a very important part of the signal. this generally for control low pass, low frequency part is very important. So, you see that the high frequency part of the signal, which was not so important for control, has got kind of folded back and it has come on the low frequency part and is now affecting the low frequency part, which is important. I am telling in very briefly. So, for this purpose you need to ensure that it does not happen. So, you need to ensure that you first cut off the analog signal such that the high frequency part cannot fold back to the low frequency part. So, for that purpose you need filters, and such filters are called anti-aliasing filters. So, you need such filters, we must remember that. Similarly, this also we have seen that we need to decide whether we are going to realize the PID algorithm in the position or in the or absolute, or in other words, or in the velocity form or incremental form. There are certain advantages with respect to auto manual transfer. There are certain actuators which will take incremental outputs. So, that needs to be decided. Sometimes, typically as we have learnt electronics also, we have seen that suppose comparators. So, comparators, if you have ideal comparators, then the output will keep on switching, right. So, therefore, we put a either a hysteresis or a small dead zone around the 0 point. So, we say that if the error is little bit here within this zone, then I am not going to I am going to keep my control output as before. So, you put a hysteresis, let me draw it clearly. So, you have an input output characteristic and you have a hysteresis curve. So, you have you say that if the error is in this zone, then I am going to basically maintain. So, if I was here, I will maintain unless the error goes out of this zone, and then I will. So, this is a hysteresis switch, right. Now, you can have a smooth hysteresis comparator, you can have something like this also. So, you say that I am going to keep the gain and then slowly change the gain. So, in this zone the gain is, the output is not switched. So, these things can be done to avoid noise, of course, because maybe you can actually tolerate that much of error, and otherwise it will unnecessarily be all the time moving the actuator because of noise. So, the actuator, so for some actuators this may not be good. Then you need to provide provision for manual bias. Manual inputs are very important, and you may like that the operator will sometimes provide manual bias. That is, if the operators are very experienced and they themselves can act sometimes as very nonlinear and sophisticated controllers. So, if he does not like the PID output, you might like to give him an opportunity to change it. Having said this, so these are typical implementation features, and now we will come to some facts on control. I wanted to start with the early tasks in control, because these are the parts that we generally in an undergraduate control course we never pay attention to. Neither have I paid attention to them here, but at least let me mention that these are very important tasks. So, first of all, selection of manipulated variables, which variables are to be manipulated, selection of controlled variables, which variables are to be controlled, selection of extra measurements sometimes required for choice is required for achieving good control performance, like disturbance rejection, as we have seen in the case of cascade loops. So, how are you going to do the cascade, which are the variable you want to sense and feed it as an inner loop feedback, you need to understand that. Selection of control configuration, that is how you are going to connect the controllers and the sensors. So, are you going to connect it in cascade with feed forward, or we have seen some special features like Smith predictor. So, These need to be done. And selection of controller types, whether you are going to use a set of single loop controllers or whether we are going to use multivariable controllers, or you are going to use a set of single variable controllers with a decoupler. So, all these things, these choices need to be made, and only after that will come the question of, once you have selected these, then will come the question of setting, I mean the control loop design, which we pay so much attention to. So, that comes at a much later stage. This is something I wanted to mention. However, it turns out that many of these questions are generally for given class of plants, these questions are generally settled. That is, if you are trying to control a reactor, which of the variables are to which sense is generally well known, right. So, but typically when you have a large plant, this may not be so clear, these options. So, next you have to find out. So, once you have done that, roughly you need to set the control objectives, that is, you need to know where you want to, which are the variables you want to control, in what way, and where do you want to set the values, such that you have good performance from the plant, and generally performance is measured in terms of money, right. So, you have to once you broadly understand the operational objectives, you need to quantify them. So, you need to actually set values which will minimize some scalar cost, right. Scalar means the single overall cost of operation, in perhaps expressed as rupees per hour. So, you need to also understand that the various constraints on flows. If you want to do that, you need to identify the constraints on flows, the various equipment constraints, actuator input constraints, and you also need to understand the product specifications. That is, what are the let us say product composition bounds, or whether the product dimension bounds. So, these are very important to be identified before the control objectives can be specified. Only after that you can aim, you can even start doing a controller design. And it turns out that cost J, that is the cost that you want to minimize, generally depends much more on steady state values of variables, especially in process control such as flows, because processes are typically not all the time oscillating, right. They will oscillate once in a while, but most of the time they are going to stay in their steady states, and therefore it is the steady state values which mainly decide the cost. So, this also needs to be identified, needs to be understood for people like us who pay a lot of attention to dynamics, but sometimes ignore the steady state operation. I want to emphasize that it is the steady state operation that generally decides cost of operation in a process control plant. Now, this cost optimization, to what extent it is possible, that depends on the degrees of freedom. Now, what is the degrees of freedom? Degrees of freedom basically it tries to answer this question, that suppose you say that, okay, I have these as, this is the plant, these are the governing equations, these are the things which can be controlled or rather manipulated, those are the things which cannot be manipulated, they are given to us, they are disturbances, some feed coming from at some flow rate or some temperature, no control on that. Then given this situation, is it possible to independently set values for, let us say, some temperature and some level? So, such questions, what is possible, that is degrees of freedom, that is what is possible to achieve, what kind of control objectives are possible to achieve given the situation with control. So, that is very important to understand before setting the control objectives. For example, if n is the number of process equations typically equated to the number of states, and f is the number of variables, and ND is the number of externally constrained variables, external or constrained. Sometimes they may be constrained in the sense that you cannot move them because of certain specifications. Sometimes they are externally coming, just like I said, some flow of some feed. And if n star is the number of control objectives or specifications, typically we are talking of steady state objectives. So something should be maintained at this value constant. This is one control objective. So if you have n star number of such objectives, then the degree of freedom is typically called f minus n minus nd. Basically what? That is, you have f number of variables, free variables. Now n of them, so I mean ideally you would have f degrees of freedom, because these are f variables which could move in the space, but because of the n equations they are first constrained, so it's f minus n, right. So if you have 3 variables and if you have 2 equations, then only one particular linear combination you can assign, or one particular variable you can assign, but you cannot assign 3 variables independently to satisfy these 2 equations, right, like that. So then it becomes f minus n, and then more than that, then of these f minus n, some more other degrees of freedom are lost because some of the variables are externally set, so you cannot vary them. So then the remaining degrees of freedom are f minus n minus nd, and that must be greater than the number of control objectives. So if it is, if the number of control objectives is equal to that, then your solution, you will get a unique solution to the control problem. If it is more than that, then you cannot satisfy it, because you have more number of equations than unknowns, and if it is less than that, then you have some further chance of optimization, that is you can actually bring in some more objectives. So just to give you a brief example, consider what is known as a start tank heater, basically a tank in which some flow is coming and you want to maintain the temperature of the tank as well as the level. So these are the 2 governing equations, very easy. So this is the level equation and this is the temperature equation. We are assuming that we are giving some heat input which we can control. So there are 2 equations, so n is equal to 2, there are 6 variables. So f is equal to 6. Of these, 2 are disturbances, so Fi and Ti, that is flow rate and the temperature of the feed. So we assume that we cannot, so those are lost, so 2 are lost. So from 6 minus 2 minus 2, so the remaining degrees of freedom is 2. So that means that it can take up to 2 control objectives. So therefore if we want to set if you want to set T and not F, T and H by controlling Q and F, this would be possible. So this is what degrees of freedom is about. Similarly, you see that sometimes typically in a control loop you have typical control loop that we consider are actually 1 degree of freedom. This is very important to understand. So you see that this is a typical control loop, right, in which several disturbances may be acting here as well as RS. So what is it that we want? We want, let us for the time being forget about these 2 and consider only this one. So what do we want? We want that good set point tracking, so the response Ys by Rs we want to shape, and we want to, at the same time we want good disturbance rejection, so this response Ys by D0s also we want to shape, but that is not possible because this is a 1 degree of freedom controller. So using CS you can either you cannot select both of them independently, right, that is obvious from the equations. So this is what it says that this is the transfer function between Ys and Rs, and this is the transfer function between Ys and D0s. So you see that if you choose CS, this gets fixed, suppose. So you choose CS to design your disturbance response, then your set point response is fixed, you can't change it. So you have only 1 degree of freedom. You can only set the response to one variable, right. So, or vice versa, if you are choosing CS to get a particular reference response, then your disturbance response is decided. Now, you could improve this situation by having this. So, for example, in this case there are 2 degrees of freedom. Why? Because you have introduced a set point pre-filter. This is called a set point pre-filter. So, what you are doing is you choose CS to assign a response to D0s, and then once you have done that, then you choose HS to assign to shape the reference response. Although there are constraints, still you cannot have arbitrary responses realized through this structure, but still you have now created 2 independent avenues for shaping the reference as well as shaping the disturbance. But remember that still you don't if you choose only one C, then you cannot shape your response to D0 and DI and DM simultaneously. You can do it for only one of them, right. So, you see these have to be realized to be able to choose the control structure. So, if you really so this tells us that if we want to assign independent disturbance and reference set points, then we cannot use the conventional control structure, because that is 1 degree of freedom, right. So, similarly, suppose we have 2 options. We actually have to simultaneously control a number of process variables. So, we have options. So what are our options? That either we could use a set of single loop controllers, that is manipulated variable A controls variable B, manipulated variable C controls variable D. So, A to B, one single loop controller give feedback of B and drive A, give feedback of D, drive C. So, you have a number of set of single loop controllers. Compared to that, you could, what is the other option? The other option is have one big multivariable controller which will take all the feedbacks and which will drive all the actuators, and it is a multivariable system. This is more modern. So, when do you do what? So, if you have non-interacting processes, you see that you are actually when you are, if you have a single loop controller, then when you are trying to control one process, one variable, you are not you cannot take care of the fact that a change in this variable can cause a change in another variable. This fact cannot be considered. So, if there is interaction between the variable dynamics, then set of single loop controllers can be very problematic and should not be used. Similarly, you may have to maintain constraints over several of these variables, but then each controller is actually controlling only one. So, then if you have such constraints which keep changing, then it is very difficult to use a set of single loop controllers. So, I mean, on the other hand, tuning is very simple. There are some plus points, that is you need to in fact they are used, and you can use it in various situations where there is not significant not interaction or constraints changing, dynamic constraints. So, you need your modeling requirement is low, you can build models by simple experiments. They are generally simplicity, general plus points are simplicity. On the other hand, you need to determine pairing. This is very important, that is which manipulated variable you will choose to set up a loop with for which controlled variable. This is called pairing, pairing outputs to inputs. So, this is an interesting point, and people have various methods. We did not study them, but this needs to be done. Similarly, it turns out that you have performance loss. You cannot achieve such control, such good control as you can with multivariable control. And when you have active constraints, then you have very complicated logic. You must have above this set of single loop controllers, you must have supervisory logic, which will look at all these single loop controllers and probably carefully manipulate the set points. So, such additional logic is required. So, all the it is not that simple. On the other hand, if you have multivariable controllers, then process interactions as well as constraints are handled very seamlessly. Actually, things like MPC, model predictive control, which are very popular in the industry today, are control methods. We did not study MPC. Are methods which are designed to handle multivariable processes with interactions and having constraints. So they are all built into the method and they are handled very efficiently. All right. So you have significantly improved performance in presence of interaction. You have easy handling of feed forward control. Again, feed forward is tends to make the system multivariable. You have easy handling of changing constraints as we have mentioned, and it requires a multivariable dynamic model. Tuning is obviously difficult, much more difficult than a set of single loop controls. Difficult to understand, less transparent, and this is the important thing, that failures can be very damaging. So what happens is that is you have put all the loops now into one box. So if that box fails, then the complete controls for your process is lost. This needs to be understood, and so this could be a major reliability threat, having a multivariable controller. So sometimes you need redundancies. Performance in a control loop can be limited either by sensor noise. Sensor noise limits the closed loop bandwidth. If you increase the closed loop bandwidth, the noise will go to the output. If you have sensor bias, this we have discussed, exactly same bias, especially in unity feedback control, exactly same bias will appear at the output. Sensor dynamics, sometimes some sensors, for example thermocouples, they are not directly put into the process, they are actually put through a well. So that well, for the heat to flow through the well, it takes time constants, and such time constants can cause stability problems, right. They can be sometimes cancelled by high pass filtering, but again that will build up noise. So there is no escape, you have to pay prices. Sensor non-linearity, sensors, if the sensors are non-linear, for example let's take an orifice meter sensor. It has a square root law in its basic sensing mechanism. So if you take it as a linear sensor, then what happens is that the process gain keeps changing depending on where you are operating. If you are operating at 100% flow, then there will be one process gain. If you are operating at 20% flow, there will be another process gain. So the controller gains needs to be set conservatively. So you will have to for stability considerations, if you are setting a constant gain controller, then you need to set the gain which will work for all the processes all the process gains without causing oscillation. So obviously now you will set the gain low, and when the process gain will become low, then it will lead to sluggish behavior. Sometimes this can be very nicely cancelled by having an inverse nonlinearity in the actuator, so that in the overall loop the sensor nonlinearity gets cancelled by the actuator nonlinearity, and in fact it happens by using valves, because valves have inverse nonlinearity sometimes. We are going to see all these later. Similarly, for actuators you can have saturation. Saturation will actually limit transient response, because you are not, how do you move a system fast? By giving it a lot of input and by giving it fast. So you need good input and you need rate limits, you need high rate limits, that is you can jack up the input very fast. So if you have any of these limits, then you cannot push the plant hard enough and you lose in transient response or closed loop bandwidth. Similarly, sometimes resolution, some actuators cannot make small movements either because of stick slip motion. So if they move it, they will move and then they will get stuck. So for such, if you have such stick slip motions, then the actuator because of resolution it keeps oscillating. So it will move there, that's actually too much correction, it will come back again, it will move there. So it keeps on doing this, and that causes oscillations. So typically such resolution problems are caused either by digital actuators like step motors, or they could be caused by stick slip friction, and the effect is that it may cause sustained oscillation in closed loop. Similarly, actuator nonlinearity, we have already mentioned this. Similarly, during process models, this we have already seen, time delay causes stability problems and degrades performance, gain has to be kept low, and if the time delay and the process parameters are known accurately, then some of them may be corrected, but it is very difficult to know it accurately, and the process model also keeps shifting. Right half plane zeros are like delays and model errors. So, remember that model errors are always high in the high frequency zone. So, increasing the bandwidth, you are going into the uncertain zone. So, you need to limit the closed loop bandwidth such that the models are fairly accurate. So, here we have come to the review. We have reviewed controller implementation, in under that control structures, control algorithms, we have seen the PID equations and the control hardware and the software. We have also looked at control performance and seen that what kind of performance can be expected is reasonable to achieve. We have seen the various kinds of plant dynamics and constraints that can affect control performance, and we have seen the hardware and software features which will limit performance. So, that is of course algorithms. So, you might ponder on these questions, for example, what kind of processes single loop control is likely to be effective. So, can you give an example? Some typical features of an industrial controller, or can you state the different forms of the PID control law and make their conversion? For example, 3 to 1, form 3 to form 1, we have not yet done. Can you look at that? Explain in what ways a sensor can limit control performance and sensor or actuator, and compute the degrees of freedom in a heat exchanger. This is a nice problem. So, compute take a standard heat exchanger with bypasses on the hot and the cold flow, put valves on them, and then try to compute the degrees of freedom. So that is all for today. Thank you very much. Good afternoon. We are going to start lesson 18, which is on a new subject. It is a new module on sequence control. So, we are going to have our first introduction today on sequence control, on the kinds of controllers that are used for sequence control, namely programmable logic controllers or PLCs, and we are going to take a first look at the programming languages, the languages which are used to specify control programs for PLCs. So, as usual, we will first look at the instructional objectives. So, after learning the lesson, the student should be able to state 3 differences between analog and sequence control. This is important because traditionally an electrical or manufacturing or chemical engineering student is typically exposed to analog control.